principle, you can split polymers, capacity of Young's modulus, by tensile strength, by thermal expansion, by resistance to diffusion, good chemical resistance, temperature dependence, low miscible surface temperatures, durability, diable, malleability. Here we have some statistics about polymers, because of production and content and types, but we will discuss it later in sections. Central relevant organic compounds that are created either by modifying a molecular by natural substances, so by chemically combining of molecular basis building blocks of monomers through various chemical reactions. We can describe the polymers as with the basic unit monomer. The polymers are constructed is using the space unit, and we can divide them in three types, like a non-branched linear structure, branched, and cross-linked. Depending on the type of monomers and the production process, the resultant monomers have different sizes and shapes. Of basic concept of chemistry. So from the periodic table of elements, the main element which is used in polymers is carbon. Basically, it's chemical bonding models. So basic two groups are metals, non-metals. Definition of them is ionic bonds. So the metals have metallic bonds. Metals models. So the history they have changed. So we have here a concept of atom Cretus. First modern atomic theory according to Dalton, nuclear shell model according to Rutherford, the famous energy level model according to Bohr, and spherical cloud model. But there are definitely more types of them. So here are only the main ones. The best is the spherical cloud model. Here we have an example of one nitrogen atom. So here we have a scheme of atomic nucleus and atomic shell, spherical cloud, the light blue color is half occupied, and with a dark blue color, the spherical cloud fully occupied. Some additions. Loads and balance formulas. Here we have a scheme of different periods and occupancy. this now. So atomic bonds. In the overlapping areas, electrons belong to both atoms. The common electron pair is called a bonding electron pair. This type of connection between atoms is called atomic bond or electron pair bond. Formulas in these notations are called valence formulas or Lewis formulas. The examples of atomic bonds are here oxygen. To be a noble rare gas, the oxygen atom will need 2 electrons. Each oxygen atoms provide 2 bonding electrons. And here we have a double bond. In nitrogen example, we will need 3 electrons to get a noble gas. Each nitrogen atoms provide 3 bonding electrons. As there is a triple bond between the atoms, each of which has a free electron pair. Here we have atomic bonding example is metal, CH4. Electrons correspond to the one dash each, as we have said before. The whole carbon atom has 4 electron pair bonds. Carbon frequently bonds with a carbon or with hydrogen. But bonding with oxygen, sulfur, and nitrogen, others is also possible. Secondary valences forces of attraction due to electron displacement. Secondary valences are weak bonding forces between individual molecules, and there are basically 3 types. The first one, van der Waals bonding, force between nonpolar molecules, a weakest secondary valence. The dipole and dipole interaction between 2 dipole molecules depending on their dipole energy. Hydrogen bond is the strongest secondary valence between a positively charged hydrogen atom and negatively charged atom is non-bonding electron pair. Secondary valence, as example, it's the famous one of water. The hydrogen bonds responsible for boiling a point of water and also stabilize, for instance, protein molecules or DNA. Secondary valence bonds. You can see this red dashed line. The plastic bonding types. The first type, chemical bonds within polymers. Second type, cross-linking of the polymers through chemical bonds. Third type, interaction between molecules. The fourth, mechanical bonding between different molecules. Here we have a table of bonding forces. So it's a column type and bonding energy in kilojoules per mole. So we have 3 chemical bonds, covalent from 150 to 150 kilojoules in mole, metallic and ionic. And we have second group of intermolecular interactions. So the famous van der Waals forces from 2 to 50 kilojoules per mole in hydrogen bonds. Bonding forces, influence of temperature on the stability of primary and secondary valence bonds in thermoplastics. So in the X scale we have a temperature and Y bonding energy. For primary valence bonds, the higher gets temperature, the bonding energy is constant. For secondary valence bond, we have a working range between two temperatures where bonding energy is constant. But if, for instance, we have a temperature which is lower than T1 or more than T1 plus, it's more range. It's a bonding energy gets lower with temperature raising. So macromolecules, here we have some examples of polymer topologies. The A is a linear, B is a stair-shaped polymer, C is a long and short chain branched, D is a cone polymer, E is hyperbranched, and F is so-called tetramer. In macromolecules, we have three tactility types. So it's atactic, isotactic, and symbiotic. Monopolymers, copolymers, and blends. Monopolymers, when basic units are all the same, statistical or all random polymers, alternating polymers, block polymers, Kraft copolymers, and polyblends. So the basic principle of plastic production is crude oil distillation, taking ethylene, propylene, ethylene, polymerization. So the basic principle of material production is cracking. We have a very long molecule, for instance, hexadecane, and within the cracking, we apply pressure and temperature to get different products like ethane, pen, butane, and heptane. The principle of material production, steam cracking. So in order to be able to use this process, there large field of different production lines, which takes around certain football fields. Here we have a similar diagram of water production. So for crude oil, using catalytic cracking, we get ethane and propane. From ethane, we can get polyethylene, PE, or vinyl chloride. And from vinyl chloride, we get polyvinyl chloride, or famous abbreviation PVC. From propane, we can produce polypropylene, PP, acrylonitrile, and polyacrylonitrile. And from propane, we can also get acetons and polymetic methacrylate, or type we know. So this is one of the most important slides in exams, classification according to the polarization mechanism. So we have to know there is three basic steps: polymerization, polykondensation, polyaddition. Polymerization is a chain grow reaction. Two molecules of styrene. Within the polymerization process, we get polystyrene. The polykondensation polyadditions are step growth reactions using terephthalic acid and ethanol or glycol. Using polykondensation, we get polyethylene terephthalate and water. In polyaddition, we use polyalcohol with polyisocyanate. Since the polyaddition, we get polybutyrene. Polymerization and effects. Radical polymerization uses chemical radicals to break the double bond. Thermal polymerization using slow pressure till radicals are formed. Ionic polymerization, in this case, either cations or anions as active centers. Coordination polymerization, activation of monomers through catalysts. As advantage is tactility of polymers can be controlled. Home and copolymerization, one or several monomer types. And it contains supporting reaction, rose, niche, condensation, creates polyamides, polyesters, nanoplastics, aminoplastics, and silicones. It started by catalysts, for instance, acetone base. Byproducts: water, hydrochloric acid, alcohols, or ammonia. There are three types of polykondensation: melt condensation, solvent-free reaction of the reactants. When melting, solvent polykondensation reaction takes place in a homogeneous solution. Interfacial polykondensation reaction takes place in the interface of two immiscible phases. Polyaddition, like polykondensation, produces polyadducts, while polykondensation has byproducts. For instance, water. This is not the case with polyaddition. Catalysts are required to initiate polyaddition. There is a shift of hydrogen atoms from one functional group to another. The most important products are polyurethane, polyurese, and epoxy resins. According to the polymerization mechanism, to find natural substances, synthetic plastics, polykondensation, polyamide, polyester, polycarbonate. In polymerization, we can produce polyethylene, polyester, and PMMA. Polyaddition, we can get polyurethane, polyurethanes, epoxy resins. Discussing the groups of polymers, we can divide them to behave in three main groups. Thermoplastics. So the polymers behave like chocolate in different temperatures. The thermosets behave like crackers and elastomer or rubber, which has a similar behavior when temperature changing, like gun bears and this. Basic principle of materials, types of plastics, or the thermosets. Tightly cross-linking networks as intentions have characteristics. They are not the slow thermal expansion thermal position without melting. So very soon below the biscuits rockers. Real snaps of plastic elastomers or scooter rubber are weak in thermonuclear forces. Their characteristics, so they're soft, malleable, thermal decomposition without melting. Here we have a primitive drawing of these molecules. So for these crackers, we have triangle type that in elastomers purpose we have a spiral type molecules which are soft and quite hard. In thermoplastics or which behave like a chocolate, have two types of the amorphous thermoplastics. So like a gelatin, for instance, so it is a PVC made in PVC and semi-crystalline thermoplastics. So it is BDF. There's of protocols. Here we have protocols. Well, semi-crystalline. So it's a combination of those and just saying lots of morphology of those properties. Here we have example of structure. It's a glass transition temperature. The x-axis we have temperature in Celsius degrees, and in y-axis shear modulus G in megapascals. So in the secondary transition, structure, we have usable range where shear modulus is approximately constant, and on last transition temperature dg, it's suddenly decreases. Thermoplastics properties as they're transparent, brittle, hard elastics behavior below G, so last transition temperature for thermal expansion, lower solidification, shrinkage. In terms of morphology and the properties, here we have semi-crystal structure example, and we have here Tm, last transition temperature and crystal melting point. Also shear modulus G. Here we have this usable range. So here we have a TG and the first point, which is called the glass transition temperature, and Tm is the crystal melting point. Here, two approximate plateaus of quite constant shadows. So this is a range ranges. Just So the properties of semi-crystalline plastics are high stiffness and stability of the crystalline base. Stiff beyond the glass transition temperature, high resistance to wear, high density and greater solidification shrinkage. Calculating crystallinity is similar moment. So we have here a large letter crystallinity, which is measured in percentage crystallites, delta H, large H, F, index F, measured heat of fusion of the sample, and delta H with large K, heat of fusion of all crystallites. Relevant. You can see it from the table. So the crystallinity percentage is measured heat of fusion divided by heat of fusion of pore crystallite, should be given and times 100%. Calculating crystallinity, least C measurement. We have crystallinity 14.95%, integral normalized value delta H 90% and peak. Type of morphology and superstructure. Here we have example of amorphous structure. So it's a special felt structure and rotation after processing. Here morphology for semi-crystalline structure. These water structures after processing are pointed in one direction. So they are called micelles. Here we have disordered micelles and ordered micelles. Semi-crystalline materials, typical degrees of crystallization for polyethylene from 70 to 80%, and polyethylene abridged. We have this value, polypropylene isotectic, polytetrafluoride, polyamide, polybutylene terephthalate, polyoxymonophthalate. Influencing of morphology on the properties. Here we have example of semi-crystalline structure. Amorphous and semi-crystalline structure at the edge of the component. Here we have a slow cooling above and below we have a rapid cooling. Morphology of polymers. So thermoplastics have in section morphology structure macromolecule and cross-linked, which we can divide in amorphous and semi-crystalline. Solid state characteristics at room temperature for thermoplastics are brittle and tough. Temperature characteristics are visible. Glass transition temperature exists, and chemical physical characteristics are soluble. And thermoplastics can describe as with analogy to chocolate, In thermoplastics and thermoplastic elastomers, we have a non-cross-linked structure, rubber is solid state, room temperature. It's a fusible, last transition temperature is in part, and it's also solvable. For elastomers or rubber, we have structure chemical bond, white mesh cross-linked. It is a rubbery solid state characteristics at room temperature, and it's fusible and not soluble in thermosets, or because we have lightly cross-linked. It's brittle and hard at room temperature. Infusible and difficult to swell, so it's not soluble. Expensive relates the properties of plastics. Here we have mesh of long chains and short chains. So in long chains, we have robust impact resistance or shockproof material, but in a short chain, it's less robust and brittle. So it's short chains. The short chains can be destructed easier. Morphology for amorphous and semi-crystalline thermoplastics. Amorphous and semi-crystalline. In amorphous group, we have this highest temperature, PS, PS pay, PC, ABS, SUN, ASA, and PMA, and the lowest temperature PS and PVC. In group semi-crystalline, the highest temperature is 2 pi IPEPS and LSP, IPA, PPT, D, which is used for bottles, polypropylene, instance, for flower pots, and polyethylene for bags is the lowest temperature. So as we have seen before, there is no plastics types which are excellent in all directions. So we have to choose the polymer systematically. So first we have to determine thermal requirements, chemical requirements, section-based polymer, mechanical requirements, selection of fillers and reinforcing material, then coupled to other requirements, selection of additive, and we can get most appropriate material. Here we have a data sheet for one of BASF production. So it's just example. Material data and testing. So we have to determine mechanical properties like tensile strengths, impact resistance, Young's modulus, shear modulus, and creep modulus. So mechanical properties is a tensile stress. So when we pull the example of material in the sides, then we have stress intensity factor, Okay. And stress and staging for environment. Chemical properties change in shapes under mechanical stress. Here we have in first column time of change in shape, time dependent, reversible, solidifying, wild point, and examples. So for elastic deformation, change shape, it's not time dependent, but it's reversible, and it's not, there is no solidifying or yield points. These are all materials. In crystallines, plasticity, there is a solidifying and wild point, but there aren't time dependencies and reversibility. So this is our metal. And here we have data for a creep, viscoelastic deformation, viscous flow, and vertical flow. Examples. Here we have multi-purpose test basement, 1A, and other test basement for tensile tests. Multi-purpose test basement according to the certification and test which can be produced using this specimen to perform various tests. So it has 20 millimeters and length 150. And using this sample, we can do bending stress, impact stress, heat resistance, pressure test, and Young modulus. Pressure test according to this stratification, density measurement, and hardness measurement according to this parameter. Section mechanical properties can test setups to determine impact resistance. So it should be impact tests, impact sense, and impact resistance. And the sample is 2 points, and we apply here strengths and smooth tensile impact tests. We have tensile impact stress. So each gets from this holding base isot impact strength tests. So when we have here a sample fixed in a gap and we apply strengths to the side and impact penetration tests damage. So it's similar to the breach when we put the sample horizontally. So we'll clipping these edges in the gaps and apply stress vertically. So here we have a picture of tensile stress. We have a stress strain diagrams for different plastics types. So tensile stress for group polymers. Some mechanical behavior of malleable amorphous polymer. For instance, polycarbonate under tensile load, technical stress as a function of strain and tension. Inside X have a strain, and on the vertical we have stress. So until the turbine point grows quite linearly, then we have a slight decreasing, then gets unlinearly high. We can do here elastic formation where chain rotation is changing the fracture. Tensile stress, semicrystalline. Mechanical behavior of a semicrystalline plastic under tensile load. Influence of mass on the deformation behavior. No stress as a function of elongation. So here we have for the formula for Young's models and famous Hooke law. Young's models have the second models, tangent models. Here, in one we have initial tangent modulus, tangent possible elastic modulus, with which to be of initial second modulus, 3 second modulus, and 4 tangent modulus. Here we have mechanical properties for different classes of materials and static Young's modulus in newtons per millimeter square. Say another value mechanical properties is Poisson's ratio. So the lateral strain is equal to delta height of the test spacement in millimeters divided by change in length in lateral direction. And longitudinal axial strain is equal to length the test spacement in millimeter is equal to change delta change in length in longitudinal direction divided by length of the test spacement. So the Poisson ratio, so simply defining it when we apply force on a sample vertically, so pressing it to the base, and the area where the force is applied get larger, but the length or height increases. Poisson's ratio defines the ratio between lateral strain and the axial strain. So epsilon 0 and epsilon 1 as a stress tension or compression acts on the longitudinal direction. So viscoelastic behavior, where we can define two types. First is behavior according to Hooke's law. It's a reversible deformation, linear elastic. Here we have linear behavior, which is increasing. So the higher is a strain, the higher gets stress. Visco, and here we have a cycle 1, 2. So the sum of the work is 0, and sum of heat is also 0. Viscoelastic behavior. So first it's a first reversible deformation, linear viscoelastic. Here we have a cycle 1, 2, and so on. And with reversible deformation, nonlinear viscoelastic is points 1, 2, and 3. And both of them, the total amount of mechanical work is larger than 0, and total heat is less than 0. In viscoelastic behavior, as more when the time increases, we have sinusoidal behavior between time and stress, and quite similar to a strain. So it's a period 2 pi divided by omega. And divided in 5 groups. Energetic change in mass, expansion, compression, formations, optical analysis, dynamic mechanical analysis. Remote analysis, ASC. So this abbreviation means differential scatter calorimetry, used to measure the following properties. Simple, so it's melting point, gas transition, specific heat capacity, enthalpy, isothermal crystallization, crystallizations, cross-linking. Here we have a measuring cell with a reference and sample. So the heat flux sensors, furnace block with heating, purge gas and protective gas. So the thermal analysis TSC is a determination of characteristics, material parameters, analysis of chemically cross-linked polymers, identification of polymer blends, and comparison of materials. Here we have on the x-axis temperature and heat flow, milliwatts. So TG glass transition, and we have here erythotherm heat flow and exotherm heat flow without parts, and between glass transition and crystallization point there is a plateau. So around the crystallization point there is a peak in the heat flow. Then we have a lower peak endothermic crystalline melting energy. So at temperature point Tm, and the area here is called crystalline melting phase. During the interval of peroxide reaction, we have exothermic reaction energy and cross-linking here, and then degradation. And here we have a formula which we have reviewed before. So the crystallinity percentage is a delta of measured melting heat of sample divided by delta melting enthalpy of the crystalline material, which we can get from the table. We have thermal analysis of cooling down process of second heating specific to material. In thermal analysis or TMA, we use furnace sample here, displacement L, and displacement transducer probe, and white load. In here's a picture of thermogravimetric analysis, TGA. This sample inside the furnace. The nitrogen air, exhaust air, and scale is micrograms, and temperature 10 Celsius degrees per minute. So thermal analysis, called the thermogravimetric analysis, the purpose to evaluate thermal stability of material and determine the share of fillers. Here we have a temperature dependence. Level 6, we have the strain in percentage, and on the vertical XY we have stress in megapascals. And in the second diagram we have temperature in Celsius and tensile modulus in megapascals. So shear modulus, dynamic shear modulus from torsional vibration test. So the Schubspannung in newtons per meter square is equal to Schub modulus newtons per meter square multiplied by tangent of Schub-Winkel in degrees. And shear modulus we can define with the help of a light source, a mirror, with a mass of vibration probe and fixation. Here we have a temperature dependence for Poisson's ratio. So it's increasing and between 60 and approximately 90 degrees temperature, the Poisson's ratio is approximately 0.4, and between 120 and 160, 0.5. Poisson's ratio is described as letter nu. Time dependence grip strengths of pipes made of polyethylene. So we have the time of load measured in years, and next we um, of tensile, so for different pipes, so the highest temperature, so this is the highest temperature for water. So we have so at least we have both time in this like span in newtons per millimeter square. Time dependence grip time strain cube. We have a picture of entropy elastic behavior. So when we press a polymer cube um, with help of heat, we can um, return it to the initial condition. Here transform invert spectroscopy. So infrared light sources, polychromatic, instance nuanced lamp, sample monochromator and detector. Fourier transform or infrared spectroscopy. So in Fourier transform, how to distinguish old plastics. So first we have baseline from background. Second, we have the position of maximum radiation energy absorption, molecular. 0.3, the so-called router, or two in-divided bands. At point 4, so point 4 shows an interference caused by water absorption of the air. Point 5, in the area 5 shows a dispersion caused by the diamond. Conjugants and additives. We have plasticizers, softeners, polymers, solvents, dyes, antistatic agents, stabilizers, flame retardants, and fillers. So we use plasticizers to make products softer, more elastic, more flexibility, lower the temperature range. External plasticizers, in order not to covalently bond it, to diffuse them out. And internal plasticizers, for instance, incorporated into the molecule chains by copolymerization. So plasticizers, for instance, PVC-P or PVC soft. So plasticizers increase the distance between the PVC molecule chains, and phthalates, among others, are used as plasticizers. So fillers, the reasons to use fillers to improve the mechanical properties, reduce costs, adjust the density. And we have types of fillers: calcium carbonate or chalk, natural fibers, glass fibers, wood flour, talc, and others. Influence on the fiber content and the mechanical properties. So the more on the horizontal x we have elongation epsilon, and on vertical x the stress, and the more we add fiber, as more is stress or elongation using. In our next video, we'll talk about plastic types, and I think we will finish now.